All right, so we got the notes for section 6.3, which deals with parametric equations and motion. So we got some definitions here, parametric curve, parametric equations. So the graph of the order pairs x equals some function of t, comma, y equals some function of t. Our function is defined on interval I of t values as a parametric curve. The equations are parametric equations. The variable t is referred to as the parameter, and I is the parameter interval. So typically this happens if you define x and y in terms of a third variable t. When we give parametric equations in a parameter interval, we have parameterized the curve. Our parameterization of a curve consists of the parametric equations and the interval of the t values. So lots of words there. Okay, so example one, for the given parameter interval, so that's this stuff here, graph the parametric equations. So typically you do this with a modified t-table. So you column for t, column for x, column for y. So our t values are running from -3 to 1, so -3, -2, -1, 0, 1. And that's going to plug my equations in. So x is t squared minus 2, so if this is -3, that's 9 minus 2, so 7. And you just work your way down. So if t is -2, that's 4 minus 2, so that is 2. If x is 1, 1 minus 2, or -1, 1 and minus 2 is -1, 0 would be -2, and 1 would be -1. I repeat the process for the y's. So y is equal to 3t, so that's -9, -6, -3, 0, 3. So these are far right columns are my ordered pairs. So over 7 down 9, over 2 down 6, -1, -3, -2, 0, and -1, +3. Now when you graph a parametric equation, you actually go in the order you plotted your points. So that's the graph of the equation. Notice you do not go outside of your points. Like you don't extend these as lines because you're restricted to those values. So -2 to +3. So same thing. So t, x, y. So -2, -1, 0, 1, 2, 3. Some of these repeat, like this one. It's the same equation, so I can just copy the values down. -1 is at -1, comma, -3. 0 is -2, 0. 1 is -1, comma, 3. So if x is 2, that's 2 squared is 4. Minus 2 is 2. This is going to be 6. And when t is 3, that's going to be 7. And this is going to be 9. And then just plot your points again. So let's see here. +2, -6, -1, -3, 0, -2, or -2, 0, -1, +3, 2, 6, and 7, 9. And then connect your dots. Looks like that. And then the last one, which I think we've actually done all of the points already for. -3, -2, -1, 0, 1, 2, 3. So this was 7, -9, 2, -6, -1, -3, -2, 0, -1, +3, 2, 6, and 7, 9. So pretty much just copy the previous table. No, that's not. Yeah. Sorry. So 7, -9, just down here, 2, -6, -1, -3, -2, 0, 2 to 6, and there. So then you have, which if you look at the curves, this final one is just the combination of the previous two. They graph different chunks of it. Okay. So it is possible to eliminate the parameter, and that just returns you back to a regular Cartesian equation with just x's and y. So eliminate the parameter, identify the graph of the following parametric equations. So typically what you do is you're going to take your x equation, solve it for y, or solve it for t, and then plug that in over here. So this equation, I need to get t by itself. So subtract 1 across, so x minus 1 is equal to -2t. Divide everything by -2. So -½ x plus 1/2 is equal to t. And then this whole equation goes in for that t. So y equals 2 minus negative half x plus half. Notice since I made a substitution, I put parentheses around it. That's just to keep myself clear and not to lose that negative sign. So 2 plus half x minus half. So y equals 1/2 x plus 3/2. This is a straight line, or a linear equation, mx plus b. All right, so for 3, eliminate the parameter of this stuff. So we're going to take our x equation, solve it for t, so we need to add the 2 across. So x plus 2 is equal to t squared. Let's see here. And then what I need to do is take the square root. So x plus 2 square root is equal to t, and then that gets plugged in over here. So y equals 3 times the square root of x plus 2, plus minus. So there is your lovely equation. This one would actually draw a parabola if you actually tried to graph it. Might be easier to think about it as, so that's bringing the 3 across and squaring, give you this, which would be y squared over 9 equals x plus 2. Then bring the 9 back across. Typically, if you have only one variable, it's a parabola. If the y is squared, it's actually tipped on its side. All right, and the last one here. So let's see here. How do we want to handle this? Let's see. I don't really want to do this with... So typically, if you have 2 different trig functions, we're going to use this trick. Because what it's going to let me do is get rid of my trig functions. So this would be 4 cosine t. This would be 4 sine squared t. I could factor the 4 out, which gives me cosine squared t plus sine squared t. But this is a Pythagorean identity. Sine squared plus cosine squared, that's equal to 1. So this is what your graph would actually be. Now, you can do goofy stuff, like I could have solved it for, so I could do x over 2 is equal to the cosine of t. The inverse cosine of x over 2 is equal to t. So y is equal to 2 times the sine of the inverse cosine of x over 2. And let's see, whoops, what that graph looks like. Sorry, I'm typing my calculator. 2 sine inverse cosine of x over 2. Right? Yep. For some reason, it won't let me draw it. There we go. So you can also do it that way, which is not usually the cleanest way. It's a circle with radius 4, which this equation will give you. But if you say have 2 different trig, if you have 2 different trig functions, that's typically what you're going to do. Use x squared plus y squared. Okay. So lines and line segments. So you can write a line as a parameterization. What you end up doing is essentially creating 2 equations for x and for y. So let's see here how to explain this. All right, find the projected line through the points, -2, 3, and 3, 6. So my x value is equal to, and my y value is equal to So this is going to be, so we start at -2. So it gives me a -2 there. And the change in the y value is 5, so plus 5t. And this one's going to be 3 minus 3t. No, plus 3t. So it would be your two equations. What you really want to do is, if you can think about in terms of vectors, you have some vector xy, and you start at your initial point, -2, 3, and you're going to go, so here, you're going to multiply by the parameter, and this is going to be x2 minus x1, so the change of values, y2 minus y1, so it'll look like this. So this would be x comma y equals -2, so sorry, that value is delta x. This is x1 and y1. This value here is delta y plus 5t comma 3t. So x comma y. So when you add vectors, you add matching components, so -2 plus 5t comma 3 plus 3t, and then you can break it apart. So x has to equal the first part, so x equals -2 plus 5t, y equals 3 plus 3t. So that's where those equations come from, if you think about it in terms of slope or whatnot. So this number here is just the change, so initial plus change. Going from -2 to +3 is a change of 5. Going from 3 to 6 is a change of 3. All right, find the parameterization of the line segment with endpoints -2, 3 and 3, 6. So what this is going to actually do is we're going to have to restrict our t values. So because I want to end it at this point, so I need to figure out what t is that gives me 3, 6. So if this is my x equation, and this is my y equation, I need to find the t values that get me to 3, 6. So 3 equals -2 plus 5t, and 6 equals 3 plus 3t. So this is 5 equals 5t, t is 1. 3 equals 3t, t is 1. So this interval has to stay between 0. So zeros are start. So if I use 0, I'll always end up at a, and it goes up to 1. So the line segment has to have a restriction. A line will not, because t can take any values at once. Okay. So let's see here. Gary walks around a horizontal line. Think of it as a number line with the coordinates of its position in meters given by this equation, where t is between 0 and 12. Use parametric equations in a grapher to simulate his motion. Estimate the times when Gary changes direction. So let's see here. Yeah, so this is mostly just looking at the graph of the function, so I'm not really going to mess with this. What you can do is you can set the x value to be your original equation. And then you can set your y value to some arbitrary thing. Like if you actually make it a variable, it'll actually make it show up better. But it is possible to have your calculator graph in parametric mode. So for example, if I hit type parametric, it'll give me x and y. So x is going to be -0.1 quantity. Now if I hit my variable key, it gives me t, whoops, t instead of x. T cubed minus 20 t squared plus 110 t minus 85, and then we're just to graph this as negative t. If we draw it, we'll zoom out a little bit. Let's try zoom auto. So there's the part of the curve. So there's his motion. So, and I can probably somewhere set the range. Let me figure out where that is. Where would it be? Normally it's in the setup, but so this is actually starts at 0 and goes to some other arbitrary number. You'd have to change the scale to get it to be the actual graph. The graph actually does something like this, so you're looking at where he changes direction at those two values. Okay, but anyway, example 8, simulating motion. A distress flare is launched from a ship deck 25 feet above the water with initial vertical velocity of 76 feet per second. Graph the flare's height against time, give the height of the flare above water each time, and simulate the flare's motion for each length of time. So to write a motion equation, your equation is y equals, so this is a projectile motion equation. This value here is your initial height. This is h0. This number here is your initial velocity, v0. And this number here is 1/2 of gravity, which is -32. So at 1 second, I would just plug 1 into this equation. So -16 plus 76 plus 75. So the thing is, 135 feet above the water. I can just keep doing this for repeating. So -16 times 2 squared plus 76 times 2 plus 75. So it's 163 feet. At 4 seconds, -16 times 4 squared plus 76 times 4 plus 75. 123 feet. So it's turned around. It's coming back down at this point. Then 5 seconds, -16 times 5 squared plus 76 times 5 plus 75. So 55 feet. Now I could graph it. So we're going to set, since this is going vertically, we're going to set our x value just to be time. We're going to let x count the time. So -16t squared plus 76t, whoops, plus 75. Draw. No, can't see it. Zoom, auto. So there's the path. So if you notice, if you trace it, it'll give you your time and give you your x value and your y value. So it hits the water after a little bit more than 5.5 seconds, because that's when the y value goes negative. Okay, so example 9. Kevin hits a baseball 3 feet above the ground with an initial speed of 150 feet per second, angle of 18 degrees with the horizontal. Will the ball clear a 20-foot wall that is 400 feet away? So we need to work in 2 separate directions at the same time. So the ball's hit at some angle. Let's see here, initial speed of 150. So I need to convert this into just a horizontal component, how fast is it traveling left to right, and a vertical component, how fast is it traveling up and down. So x and y. Well, the trick is, I know this angle. So the x velocity is cosine, so it would be, bad example. It'd be the magnitude times the cosine of my angle. Initial y velocity is the magnitude times the sine of my angle. Now, horizontally, gravity doesn't act. So the distance an object travels horizontally is just how fast it's going horizontally times the amount of time it takes. Vertically, I have to go back up to my previous equation. So the vertical position is -16t squared plus this stuff, the initial vertical velocity times time, and it's hit from 3 feet above the ground. So plus 3 goes at the end. Okay, and then let's see here. Will the ball clear a 20-foot wall that is 400 feet away. So I can use the 400 feet to figure out how long it takes the ball to get there, because the horizontal velocity is constant. And then I can plug that time into my vertical and use that to figure out if it clears the wall. So over here, t is whatever 400 divided by 150 cosine 18 is. Let's make sure I'm back in degrees. So 400 divided by parentheses 150 cosine 18. So we'll reach that wall after 2.8 seconds. So over here, just plug all it in and figure it out. So negative 16 times 2.8 squared plus 150 sine 18 times 2.8 plus 3. So this height comes out to be this vertical height will be 7.3 feet. So it will not clear the wall. All right, and last example, example 10. Jane is riding on a Ferris wheel with a radius of 30 feet, so center to edge. So if you view the figure below, the wheel is turning counterclockwise, so it's going that way. Makes one revolution every 30 seconds, so that's actually our period, in case we need that. Observe that the lowest point of the Ferris wheel is 10 feet above the ground, and Jane is at the point marked A at 3 o'clock. So she is one radius above the ground, so at point A, this distance is 40 feet, because there's 10, and she's exactly even with that. Find the parametric equations to model Jane's path and use them to find Jane's position 22 seconds into the ride. So let's see here. So our x position is going to be the radius times the cosine of theta, because when she is at 0 degrees right here, she's 30 feet out, that's the radius. The y position is always sine, but it's going to be plus 40, because at time 0, she's 40 feet above the ground. So there's your two equations. Let's see here. So we're going to need this, because we need, well, it's in terms of theta, we want it in terms of time. So the period is 2 pi. So let's see here, how can we do that? So 2 pi over 30, which would be pi over 15 is my b value. This period is, b is equal to 2 pi over p. So this becomes x equals 30 cosine pi over 15t, y equals 30 sine pi over 15t plus 40. And then you can plug your 22 seconds in. So when the x equation, when t is 22, go back to radian here, 30 cosine pi divided by 12 times 22 comes out to be whoops, pi over 15. I did pi over 12. Negative 3.1, and for the y equation, we would have 30 sine plus 40, so 10.16. Now this is relative to the so our axis is centered there. So the y value is 10.6 above the center, so that'd be, whatever it would be. Yeah. But there we go. That's the end of the section.